Good morning, ladies and gentlemen. Today I would like to present you the work with the title The Prediction of the Correct Path and Structure Durability based on the damage function approach. Before coming to the mathematical modeling and numerical simulation, let's introduce some knowledge about the modern state of art in fatigue. According to the recent work, we can see that there are several regimes of fatigue loading, and here we distinguish three parts: low cycle fatigue, high cycle fatigue, very high cycle fatigue, and we assume that this curve described by the similar equation. We'll say that it's a Baskin-like equation, and the gap between two branches, left branch and right branch, is corresponding to the bifurcation area here. If we have a look on the in-service failure due to fatigue, we can recognize some marks corresponding to the different crack propagation stages. And it often happens that crack initiated in the one fatigue regime and later propagate under the different loading condition. For example, at this picture, we see the crack initiation due to the high frequency vibration, and after, due to change in the rigidity of the element, the crack propagates under the high cycle fatigue conditions here, and it means that in order to predict such fatigue behavior, we need to develop some model with a progressive damage accumulation. The basic idea is following. We assume that the left branch of the full ascent curve is similar to the right branch, and we can write the equation that will describe the shape of this curve. For the left branch, here with the letter L, and for the right branch with the letter V. And we see that equivalent stress will correspond to a number of cycles to failure, and some constants should be determined based on the experimental data for a given material. So we assumed that at the beginning the fatigue strength is not far from the ultimate tensile strength, and it gives us the boundary condition on the left hand. When we move on the curve, we come into the so-called fatigue limit here, and it will give us the second boundary condition on the right. In the case of the right branch, when we are describing the very high cycle fatigue range, we assume that fatigue strength at 10 power 8 approximately the same to the fatigue limit here, and it gives us the boundary condition on the left edge of the right branch. And after we have a fatigue limit at a given number of cycles that is corresponding to limit in very high cycle fatigue region. And this gives us the second condition for this curve. Taking into account all these ideas, we can write the exact expression for the constant sigma L and constant sigma V. Here is presented. The power beta L and beta V is taken from the analysis of experimental data, and it corresponds to the rate of decreasing of the corresponding curve. When we are introducing the fatigue failure criteria, we do not mention what does it mean failure is it time to crack initiation or to final rupture? So in order to clarify this point, we use a special function that we call damage function with its own kinetical equation. And we do the link between the multi-axial criterion and the fatigue damage accumulation by using this function. Here you can see the kinetic equation in the shape close to Robotnov-Kachanov damage theory. And we have the structure where we have a damage function and some coefficient that is depending on the stress state. In order to determine the parameters of this equation, we can assume that crack initiation will start at a given number of cycles NL for the left branch and at the number of cycles NV for the very high cycle fatigue range. According to the multi-axial criteria, we can easily find the description for this value is given here. From another side, it means that the damage function will get the value equal to 1, and we can separate this equation with different parameters and integrate it. After integration, we'll have this expression for damage function that is vary from 0 to 1. From another hand, we'll have a number of cycles multiplied by coefficient beta b here, and the limit of integration is from 0 to NL here. The same procedure we can do for the right branch here. And according to this calculation, we can give the following equation for coefficient B. As we can see, it depending from equivalent stress and some constants of material. The same things for the right branch here. When we are using one of the multi-axial criteria, we'll have this following expression for the equivalent stress written here at the top. So, and we can use different criteria. For example, here we introduce one criteria for normal crack opening, the second one for the shear crack opening on the right hand. And after the integration, after all calculation, we'll have such equation for those two criteria. And we do the calculation in circles. In this case, we can organize degradation of Young modulus here for material. We assume that when the damage function is lower than its critical value, we have the equivalent elastic modulus with the following expression. When the damage function reaches the critical value, the material is destroyed and it cannot carry load anymore. Let's say some words about the numerical methods. So, if we have a look on the kinetic equation for the damage function, we see that with approaching material to failure, damage function will approaching to 0. And in this case, the diminution of the equation will close to 0. And in this case, we cannot use the explicit methods for calculation because equation become stiff. And in order to solve this problem, we move from explicit to implicit scheme here, and we can write in this case the analytical solution for damage function at the new time layer. So, and here we have some limitation for the step in number of cycles. We use a half of it, and see below it's written the equation for the Young modulus as a function of damage value. The numerical method is following. First, we obtain the elastic solution or elastic plastic solution for the problem by using one of the package that perform finite element method. Based on this solution, we can calculate the damage function in each node. These calculations we do with a self-developed code that is integrated in the ANSYS or Abacus or other program, and we calculate the damage function in each node of the mesh. With this value of damage function, we can recalculate the effective elastic modulus and to start the new calculation with the new parameters. At this slide, we introduce some basic examples for this model. First is a just simple tensile test with double crack initiation in normal opening crack. After we have the results for shear loading. Here we have a normal crack opening crack 2. And after we do some test with a combined loading, tensile compression with a shear, and we see that in this case we can get the crack initiation in two different modes, in normal crack opening and in shear crack opening. In order to simulate the crack propagation in torsion specimen, we prepared the numerical model with a very fine mesh in the work section of the specimen. Here, and after loaded it with a pure torsion and the resonance frequency. At these slides, we can see the progressive damage development in this specimen that is corresponding to the real fracture surface here. The depth of the crack here is limited by the section of elements, and if we will see on the fracture surface of the specimen, we have a good link between the experimental results and numerical simulation. Moreover, here we have a lateral surface of the specimen, and we see that model predicts the crack initiation in the plane of maximum shear stress with a further bifurcations to the crack propagation in the plane of normal crack. And the analysis of the criteria that destroy the element show that at the beginning it's shear stress that is leading to the fracture, and later the crack propagation is related to the normal crack opening. And coming to the conclusion, we can see that we introduce multi-mode kinetic model for fatigue failure prediction under multi-axial loading, and this model have a good agreement with the experimental data, and it can predict the change in the crack propagation mechanism For example, particularly here we show the results for torsion crack that is initiated under shear condition and after propagated under normal crack opening conditions.